when we were here learning about the multiplication principle, probability of E intersection F now has a formula, E given F times probability of F, or F given E times probability of E. So we had to apply the correct formula, whichever is applicable. Two formulas for probability of E intersection F. One is E given F times F, the other one is F given E times E. So we need to choose whichever is applicable. And we did this first problem, but I'm going to go over that quickly. So that you recall exactly how to do that. From the 52 card deck, 2 cards are drawn without replacement. What is the probability that the first is ace and the second is king? Now here the word is and. That means we want both of them to happen. So if I call E as the first is ace, F is second card is king, then the probability we are looking to find is E intersection F. Both have to happen. So we have a formula that tells you probability of E intersection F is equal to probability of E given F times F or F given E times E. Now we had to think about which one applies. The first event has to happen first. So therefore the probability that the second card is king given first card is ace is the one we can find. So probability for F given E is the one we can find. So therefore we will use this formula. So probability for F given E means E has already happened. So first card was ace, and that means all 4 kings are there. So therefore probability for the king to happen now is 4/51. 1 card is already taken, so that there are 51 cards left. So 4/51. Probability for E would be probability for the first card to be ace. There are 4 aces out of 52 cards. So the product of these will be our answer. 1 second. All right, so now the example 2 says, do the last example by permutation combination. This can be done by permutation combination too. So let's see how to do that. Now here in the permutation combination, we didn't do exactly a problem like this. We did problem like this. If I select 2 cards from the 52 cards, then what is the probability that one of them is ace, the other one is king? We did problem like that. But here, only difference here is the order matters now. The first card has to be ace, second card has to be king. So the order matters. Other than that, it is very similar to the permutation combination problems we did before. So since the order matters, the sample space is going to have all the different combinations, of 2 cards and the rearrangements as well. So you have to take all the 2 cards and rearrange and count all of them. That'll be your count of the sample space because the order matters. So therefore, count of the sample space is permutation instead of combination because the order matters. Permutation of 52, 2. And the event that we need to happen is we had to have first card ace and the second card king. So how many elements in the sample space have first card ace and the second card king? Now we can apply box method because order matters now. See, if it's combination, you cannot use Bart's method, but it is order matters here, so we need to use Bart's method. The first card has to be ace, so there are 4 aces, and therefore there are 4 ways to get ace. And there are 4 kings, so there are 4 ways to get king. So 16 cards are there with the first card ace, second card king. 16 ways are there to get first card ace and second card king. Now let's simplify the 52 2, and that'll be 52 factorial over 50 factorial, and that's equal to 52 times 51. All right, so the probability of E is 16 divided by 52 times 51, which matches the answer we found here. So it can be done by permutation combination. The only difference here is the order matters, so you have to count by the permutation instead of combination. Okay, so let's go to the example, exercise 1. This is exercise, so I expect you to answer that. 3 red balls and 5 green balls are there. 1 ball is taken without replacing. So we take 1 ball and without putting it back, we take another one. Find the probability that the first is red and the second is green. So can anybody tell me where to begin? Maybe we can introduce the events as E equal to first is red and F is second is green. So what am I looking to find? Probability of anybody? What probability am I looking to find here?
That the first one is red and the second is green.
Yeah, so what do
Right?
I write
Would
here?
it,
P of
would
what?
it be 3 out of 5 or 3 out of 8 for E?
No, don't solve the problem yet. Just tell me what to write here. P of what am I trying to find?
Would it be 8 comma 3?
No, it's not permutation. I'm trying to apply. I'm not trying to do this problem by permutation combination. I'm trying to do this problem by conditional probability method, this method that we discussed first. For example 1, this problem is very similar to that, and I'm trying to use that same method. So what probability am I trying to find here?
Would it be 3 1?
Where are you getting the numbers from? What event am I trying to find the probability for? That's my question. Or in other words, how do I write this event in set form using my sets E and F?
Probability that the second is green given that the first ball is red.
Not really. It's not say. It doesn't say if the second one is green, then what's the probability the first one is red? It's not saying that. It says what's the probability that the first is red and second is green, right?
So we're finding the intersection of them.
Exactly. E intersection F is what we need to find. We want E and F to happen. The word is and. So we want E intersection F to happen. Now, to find it, we're going to have to use the formula with the conditional probability, the conditional probability formula, because that's what we can find. We can find probability for the second one to be green, given first one is red, and things like that. So therefore, I need to write the formula, which says probability for second green F given E. This is the one I can find. I can find the probability for the second one given first has happened, but I can't find the other way around, right? So that's why you have to go with the logic. I can find probability for the second to happen given first has happened, but I cannot go the other way. I cannot find E given F. So therefore, F given E times probability of E is the correct formula to use. And therefore, what is now we find the conditional probability of F given E, which means probability for the second one to be green given first is red. That's what we are finding now. Okay, what is that?
5/7.
5/7. Because the first one was red, and therefore there are 2 reds and all 5 greens are there. So 5 green out of 8 balls, 7 balls. Now there are only 7 balls. So if E has already occurred, that means the first one was green, first one was red, which means all 5 greens are there. So therefore, probability for the second one to be green is 5/7. Now I need to find the probability for E, which is probability for the first one to be red. And what is that?
3/8.
3/8. So this product will be our answer, 15/56. It doesn't reduce. So that's our answer. Okay. Okay, now we are going to do more conditional probability problems, but we need to understand the tree diagram next. Tree diagram is a way of describing events in the proper order and along with the probabilities so that we can work out the numbers easier. And you will see that in some circumstances, the tree diagram comes in handy. And you need to understand tree diagram to be able to learn statistics later on. So let's understand what tree diagram is. Suppose that an event E and then event G will happen. Like in this last exercise, first event was taking 1 ball and second event was taking another ball after that without replacing. So taking first ball would be the first event, taking the second ball would be the second event. So when they happen in a sequence, we need to put them in the right order. So in the tree diagram, we will put a circle to begin, and then that's called the root. And then one branch will represent one event happening, E, and then another branch will represent another event, F, happening. If there are only two possible events, then these only 2 branches. If there are 3 possible events for the first one, then you have to have another branch. And then the second event will happen after first happened. So you need to branch out of this to draw another branch for the G. And G can happen after E or G can happen after F. If E and F are the only ones that can happen for the first part, then they had to be complementary. Like in this exercise 1, the first ball has to be either red or green. So if the first ball is red, then the event F would be first ball is green. You know, those are the only 2 possibilities. If there are other possibilities, then we had to have other branches. So G can happen after E, or also G can possibly happen after the F. So when we write G here, this really represents G given E. It really is G given E. And this is really G given F because this happens after F. This G happens after F. That's after E. So the second branch represents conditional probability, actually. So so if the second one represents conditional probability, then probability of both happening, probability of G intersection E, both G and E happening, is same as probability of G given E times probability of E which means what? Probability of G given E is what this branch represents. So if we know this probability of E is this. So the two probabilities on these two branches, when you multiply them, you get the probability for both to happen. Same thing here. Probability of this multiplied by probability of this will be the probability of G and F occurring, according to the formula we learned. So that's why the tree diagram makes it convenient to display all the information about the probabilities. And I'm going to demonstrate that using this example. Of the applicants to medical school, 80% are eligible to enter, 20% are not. So there are probabilities for eligibility. To aid the selection process, an admission test is administered. It is designed so that eligible candidates will pass 90% of the time, and ineligible candidates will pass only 30% of the time. So show this information on a tree diagram and find the probability that an applicant for admission will pass admission test. All right, so let's put that on a, well, I don't need to draw that. I can demonstrate that here in this picture. The first branch, E represents, see, the test has to go first. So you have to put them in the right order. Before they are admitted, the test will be given. So therefore, test has to go first. I will put a rough sketch on the board as well. So let me pick up the pencil. Okay, so from the root, I have E will be passing the test. I'm sorry, E is eligible. I define my events as E is eligible, E bar is ineligible. P is the pass the test, F represent fail the test. Eligible goes first. Let me see. Yes, because the eligibility has to go first because passing given eligibility is known, and failing given and then passing given ineligibility are the numbers given to us. So therefore, eligible, ineligible goes first. As you can see, these are the only two possible events, and so they are complementary. Probabilities of these two have to add up to 1. They're complementary. And then once among those who are eligible, how many will pass the test? How many will fail the test? Those are the two branches. So pass given eligible, fail given eligible. They are complementary. Again, these two have to be complementary. Fail given eligible. And on the other branch, pass given not eligible, and fail given, I'm sorry, the other branch will be fail given ineligible. So the probabilities are given, 80% are eligible, 20% are not. So 0.8 is the probability to be eligible, 0.2 is the probability for the ineligible. So they have to add up to 1. And then given eligible, according to the problem, eligible students pass 90% of the time. So therefore 0.9 is the probability to pass given eligible. 0.1 is the probability to fail given, because these two are complementary, so therefore that's 0.1. And probability for ineligible student to pass the exam is 0.3, and therefore the complementary part is 0.7. Okay, so now I can find the probability for passing and being eligible. The passing and being eligible, that will be probability for P given E, given eligible, times, let me erase that 1 second. The we write the probability for both to happen at the end of this branch. So probability for both to happen, that's E pass and eligible would be equal to probability for pass given eligible times probability for eligible. That will be the product of these two branches, 0.8 times 0.9, or 0.9 times 0.8. That's 0.72. Okay. Similarly, I can multiply these two branches to get this probability, and these two branches to get this probability for both to happen. And these two product will be the probability for that to happen, for both to happen. But the question is, what is the probability that an applicant for admission will pass the admission test? What is, find the probability that the applicant for admission will pass the, okay, so applicant will be, what is the probability that an applicant will pass the test? All right, let's finish multiplying these. The probability for F and E to happen, fail and eligible to happen is 0.1 times 0.8, which is equal to 0.08. And 0.2 times 0.3 is 0.06. 0.7 times 0.2 will be 0.14. Okay. Now, this is the probability for the student, for the candidate to pass, given he or she is eligible. The question is, now this is the one for the student or candidate to pass, given he or she is ineligible. Now, let me explain on the side the passing is going to happen in one of two ways. Eligible students, passing given eligible is one, passing given ineligible is another, two. So the first event has two possibilities, and then second event, passing, failing. Now what we need to find is passing regardless of whether the student was eligible or not. So probability for pass is what we need. But the pass is going to be happening after E or E bar happening. So in other words, we have this situation that pass, let me just show on the Venn diagram. The first event is E, eligible or ineligible. The outside of E is ineligible. The second event is passing. I called it P. So the probability for the entire P is what we need, but P intersection E is this part. We can find that probability. We already found it. P intersection E bar is what this is, right? In other words, ineligible students passing. So I need to add these two probabilities to get the probability for passing. So what I need to do is I need to add the probability for passing is equal to probability for passing intersection eligible plus probability for passing intersection ineligible. You can see in the Venn diagram, P has two sections, one part in E, the other part in E bar. So I need to add up those probabilities. So therefore, in the tree diagram, it's equal to sum of this probability of P intersection E and P intersection E bar. In other words, all the branches that have pass, this branch has a pass, given E has happened. This branch has passing, given E bar has happened. You have to add those two to get the probability for passing. So probability for passing is 0.72 plus 0.06. This number plus this number, 0.78. So that's how the tree diagram works. And I have what I explained here using that, to answer that question, the explanation I did here is all explained on your paper, as you can see. So E and E bar are complementary event here. The first event, E and E bar are the two events that you can have first. So the P passing, that's the second circle, intersects both E and E bar. So therefore, probability of for passing is, or the event P is equal to P intersection E union P intersection E bar, and therefore probability for P is sum of the probabilities of those sections. And that's why you had to add up those to get the answer. Okay, so if you understood that, then can somebody tell me how do I find the probability that the student or candidate fails? What number should I add up?
0.08 plus 0.14.
Right, 0.08 plus 0.14. So let's add that on the side. So probability for failing equal to 0.08, this number, failing given eligible, plus failing given ineligible, which is this 0.14. Okay, 4. And that's equal to 0.2, no, 1, 2, yeah, 0.12. Okay, so this 0.12 and the 0.78 we found here have to be complementary. Do they add up to 1? They add up to 1, right? See that? And clearly they have to add up to 1 because this one is the probability for passing, this one is the probability for failing. They are complementary. So yeah, so they have to add up to 1. So in essence, that means all the endpoints, the probabilities at the ends, probability at this end and this end, these two add up to give you the probability for passing, and probability at this end and this end gives you probability for failing if you add them. And probability,
Professor, I got 0.22.
I'm sorry. Oh, 20.
Adding 0.08 and 0.14, I got
Yeah, 20.
0.22.
Right. Thank you. Thank you. That is 22. 0.22 and 0.22 and 0.78 add up to 1. Okay, so let me go back to the tree diagram. This branch plus this branch, end of those two branches give you the probability for passing, and end of this branch and end of this branch gives you probability for failing. And since probability for passing and failing should add up to 1, basically all these numbers at the end of the tree diagram should add up to 1, right? 0.72 plus 0.06, 0.08, 0.14 should add up to 1. All of them are complementary. So those are the properties you need to understand. So what are the things, what are the properties? The first two branches are complementary. So if you know one of them, you can find the other one. And from each, at the end of on the end of that branch, if you have two branches, or if you may have three branches sometimes, but the probabilities there have to add up to 1. They are all complementary too. And probabilities here have to add up to 1 because these two are complementary. And then the probabilities at the end of the tree diagram, end of all the branches will have to add up to 1. Those are the properties. I have described those properties somewhere here, but you can see that from this example. Okay, so I have a second example here. I'm going to go over that because.
So for a problem to be a complementary event, it would have to equal up to 1.
Probability of, yes, that was, we talked about that a long time ago. Probability of any event, E, and the complementary event, E bar, have to add up to 1.
I just wanted to know, just in case they ask on WebAssign a question like that.
Yeah, of course. Complementary events add up to 1. That's, way in the past, we discussed that. So let me put that on a Venn diagram to quickly show you. See, if this is E, then remember probability of this and the probability of outside have to add up to 1 because sample space have probability 1, right? Probability of sample space is 1. So if this is 0.6, the outside has to be 0.4 because they have to add up to the probability of the sample space. Okay, so let's do this example 4. There are 3 marbles, 3 red marbles and 5 green marbles in a jar, and take 1 marble and then without replacing it, take another marble. This is same as the example we did earlier. And we did the problem without doing any tree diagram, but this problem says, show the tree diagram and then find the answer to the question. So I'm going to show the tree diagram. I'm defining my events as R1 means first marble is red. G1 will be the event, first marble is green. So there is first and the second. So I have to have the first one going first in the tree diagram. So R1 and G1 are the first event. So if you look at the tree diagram, I have R1 and G1 as the first 2 branches. And then R2 and G2, which is R2 represents second marble red, G2 represents second marble green. They have to be happening after the first marble. So therefore they branch out from the tip of the first branch. This probability is 3/8 for R1. Why? Because there are 3 marbles, 3 red marbles out of 8 marbles, 8 total. And therefore, for the G1 is 5/8, 5 green marbles out of 8, and they add up to 1, as you can see. And now R2 given R1, that means probability for the second one to be red, given first one is red. So if the first one was red, then there are only 2 red left out of 7 marbles. So that's why the probability for that is 2/7. And probability for the second one to be green, given first one red, is 5/7, because if the first one was red, then all 5 greens are there. So 5/7. So similarly, I calculated these probabilities. So I have all the probabilities available. At the tip, we write the intersections. So how do I find the probability for R2 intersection R1? What do I do? To find the probability of that?
Add R1 and R2.
We don't add, no.
Multiply?
Yes, I just remember in the previous example, I went over that. Probability for looking at the previous example on the board. Probability for the P intersection E, to find the probability for P intersection E, I have to apply this formula, P given E times E, and P given E is this probability of E is this. So these two multiply. If you multiply these two, you get the intersection. You get the probability for both to happen. So probability for R2 given R1 here in this picture is equal to, which numbers should I multiply?
Three, 8, and 2, 7.
3/8 times 2/7. That product will give you the probability for the intersection. Okay, so so similarly, G2 intersection R1 is 3/8 times 5/7, and so on. So now, if the question asks you, what is the probability for R2, which means second one is red, it's not conditional probability now. It's just simply, what is the probability that the second one is red? Then what numbers should I add up? Okay, so this branch, the tip of this branch represents probability for R2 intersection R1. And this is our G2 intersection R1. This is R2 intersection R1. And this is G2 intersection G1. Okay, so if I want probability for R2, that's second marble to be read, I should add which numbers?
Probability of R2 intersection R1 plus probability of R2 intersection green 1.
R2 intersection green 1. Just like I explained in the previous example. Here also R2 is happening here, and R2 is happening here too. Here, given R1, R2 given R1, here R2 given G1. Now R1 and G1 are complementary. R1 and G1 are complementary. So same question like before. The R2 is same as R2 intersection R1 union R2 intersection G1. R1 and G1 are complementary. So that's why by adding the probability of this and this, you get probability for R2. So probability for this number and this number should be added up to get probability for R2. All right, so I have another two examples here, but we don't need to go over them. I already those examples are enough, but you can read these examples if you like, but we don't need them. We already understand. We already went over all the facts. So the exercise 2 says 2 cards are drawn from the deck without replacement. What's the probability that the first card is diamond and the second card is red? Okay, that's very similar to the problem we just did a few minutes ago. We don't need tree diagram for this, by the way. You can draw a tree diagram, but you don't need to. Unless the problem asks for it, don't use tree diagram as a way of solving because we don't normally have to. It's a lot more work, as you can see. If you look at this example, for example, this example 7 is showing you how to do this early example. The card, which one? The problem we did with cards earlier, this problem here. To do this by tree diagram means, you're really working out more details than necessary to solve the problem. Tree diagram has to show all the details, everything that can happen. But when you're doing just manually, the way we did it before, we're just finding the one probability that they're asking for. So you don't need to draw the tree diagram to solve this problem. But if you want to show all the details for this problem, the tree diagram would be huge. It's this. Because the first card we draw can be diamond, heart, club, or spade, four possibilities. So I had to have 4 branches. And for each branch, I have to have another branch showing red and black, because the question is about red and black, given first card is diamond or heart or club. So as you can see, the tree is showing all the details, but to solve a problem, I don't need to show all these details. It's a lot more work. So you work on the tree diagram only if they ask for it. Otherwise, you can solve the problem directly without having to draw the tree diagram. Okay, so this thing I explained on the tree, that you had to add up these 2 probabilities to get the probability for R2. Now that's true even if there are more branches. So if there's another branch, let's say another branch from the root, and you have another R2 coming here, then you had to add up that also, that number, this number, and this number. So if there are more branches, then there are more numbers to add. That's what I'm explaining down here. But we don't, and it goes on. I mean, if you need the probability for R2, you need to take the probability of R2 intersection R1, R2 intersection G1, this is G1, and R2 intersection any other, if there are other ones. So if there are more branches, then more numbers to add. All right, so let's do this exercise here. A tree diagram is given, and fill in the unknown probabilities and then find the indicated probabilities. That's our question. All right, so that's, we need to do that. All right, can somebody tell me the answer to the first, you need to fill out these unknown probabilities. There are 3 branches going out of the root, and event B and C have probabilities given. So what is the probability of A? What number goes for probability of A? Anyone?
0.1.
0.1. Okay. Everybody understand why that's 0.1? Because the other 2 are 0.5 and 0.4. You add them up, that's 0.9. And since all 3 have to add up to 1, A has to be 0.1. Okay, now D and E are happening after A happens. So what is the probability for E?
0.7.
0.7. Again, that's complementary. And that those 2 have to add up to 1. So therefore, it has to be 0.7. Okay, the E coming out of the second branch, what's the probability there?
0.6.
0.6. Okay, and this one, the third E?
0.3.
0.3. Okay, 0.3.
How do we get 0.6 for the second E?
Because there are 2 branches here, and they're complementary. Okay?
Okay.
So they had to add up to 1. Same thing here. After the C, there are D and E, and they have to add up to 1. So 0.3. Now the question says, what's the probability of E given A? What is it?
0.7.
0.7. We already have it on the tree, as you can see. This 0.7 we have here is probability of E given A, because this is E happening after A happening. So that is actually E given A. So that's 0.7. Okay, what's the probability of E given C?
0.3.
0.3. E given C, yes, 0.3. Okay, probability of A intersection E.
0.7 times 0.1.
0.7 times 0.1 is correct.
0.7 would be the answer, or do we have to write out 0.7 times 1?
No, you just multiply to get the answer. 0.7 times 0.1 is equal to 0.07 will be the answer. Yeah, you can just give me the answer there. And everybody understand why 0.7 times 0.1 is equal to probability of A intersection E?
Yes.
Okay. Probability of A here and probability of E given A. Probability of E given A is 0.7, probability of A is 0.1. The product will be the probability that we normally write at the tip, which is the intersection. Okay, probability of C intersection E would be?
0.12.
Right, 0.4 times 0.3, which is 0.12, right. So 0.12. And probability of E.
would you add all the e's together or multiply them?
Right, add them. Because
Okay.
this number at the tip of this line will be E intersection A. Let me put it on the board. Um, okay, the probability of E is the question here, right? But E, sorry, let me draw this separately. So, 1 second, I messed up the board. If I draw the Venn diagram, my event E happens after A, B, or C. A, B, and C are complementary. So there are 3 other events. So let's say this is A, and I'm just trying to explain. This is B. No, A and B, A, B, C are complementary, so they cannot intersect. 1 second. This is E. So I have to draw the A and B as the following. They're complementary. So this, if I draw a line like this, the left side is A, then the right side is A bar. Okay, I had to draw that way, A bar. Similarly, there's B, and it's hard to draw all 3 of them. But you understood the point when I used 2 sets. Let me clear the board. If I draw 3 sets, the picture becomes too complicated for you. So I'm going back to 2. So if E occurring after another event occurring, then the other event is like this. Let's say this is A. Then A bar is the outside. And E is equal to E intersection A union E intersection A bar. E equal to E intersection A union E intersection A bar. And therefore, and they are complementary, these 2 do not intersect. So therefore, probability of E is probability of E intersection A plus probability of E intersection A bar. And so that's what we used earlier. And instead of A and A bar, if there are 3 complementary events, if there are 3 branches in the tree, then all 3 are complementary. So A, B, and C are complementary. Then instead of A and A bar, you will have A, B, and C. So probability of E will be probability of E intersection A plus probability of E intersection B plus probability of E intersection C. All 3 have to be added up. So that's why, because there are 3 branches here. So this number, 0.7 probability of E given A, that's that. So at the tip of this branch, we will have E intersection A, the probability of E intersection A. And at the tip of this branch here, I'll have E intersection B, probability of E intersection B. At the tip of this branch here will be probability of E intersection C, and I have to add those up. So the numbers I'll be adding up will be the tip of E, which is 0.7 times 0.1. So 0.7 times 0.1, that's the number at the tip of first E. And at the tip of second E will be 0.6 times 0.5. So I need to add 0.6 times 0.5. And then at the third tip of at the tip of third E, 0.3 times 0.4. So plus 0.3 times 0.4. So you need to simplify that to get the answer for that. Okay, so what numbers should I add up for probability of D? Again, you can add up the tip of the D here, the first D, second D, and third D here. Or what is the other way? Anybody?
One minus probability of E bar.
Right, 1 minus whatever we found here. Whatever this adds up to, complement will be the sum of the other three branches. I explained already all the ending numbers, the numbers at the end of the tree, all of them have to add up to 1. So therefore, to find the probability of E, since E and D are complementary, I can simply subtract the probability of E from 1. So probability of D equal to 1 minus probability of E, which is found in the, oops, 1 minus probability of E. You found probability of E in the part E. So just subtract it from 1. Okay, so that finishes that problem, tree diagram. Now, unfortunately, the WebAssign didn't have a problem like this in this section, but it has problem like this tree diagram in the next section. So unfortunately, I do have some tree diagram problems, but it's not complete like this. It has some questions, but not all the questions like these. So I have to give you that kind of problem in the next homework, not in this homework. Anyway, let's go to the exercise 4. So that finishes the tree diagram. Basically, everything about tree diagram is done. And like I said, you don't have to do the tree diagram to solve every problem. You do the tree diagram only for the problem that tells you to use tree diagram. The Venn diagram shows the number of elements in each section and find all these probabilities, okay? So probability for F intersection E, it says verify this is true by finding all these probabilities. We already know this formula is true, and this problem says verify that in this using this example. All right, so let me clear the board and compute the probabilities. Probability of E. The numbers given here are counts, not probabilities. Okay, so what is the probability of E? Anybody?
(20/40).
The E, yes, 20/40. Let me check the numbers 1 second. 25, 30, 40. That's the number is incorrect. I don't know why. Can you see those 3 numbers in the circles add up to 40? So sample space should have more than 40, right? I don't know what went wrong there. There should be some elements outside the circles. So therefore, I'm changing that to 50 because that's not right. All right, let's work with those numbers. Probability of E is equal to number of elements in E, which is 20 over total elements in the sample space, 50. Okay, let's keep it simply, not simplified. Probability of E, F given E, okay, what is that?
5/20.
5/20 is right. And probability of F intersection E?
5/50.
5/50. There are 5 elements in the intersection, 50 elements in the sample space. So basically, we need to verify that the product of these two is equal to this. third. So 20 over 50 times 5 over 20. So 20 cancel out, and you have 5 over 50, which is equal to this, right? Equal. So we verified it. That formula is true. Exercise 5 says 2 people are selected at random from 9 men and 5 women. Find the probability that first is woman and the second is man. Okay, so if I define my event E as first is woman, F as second is man, then we are looking to find the conditional probability, no, we are looking to find both, right? First woman and second man. So that's intersection. We're looking to find the intersection. We have to use conditional probability because that's what we can find from this problem. So do I write E given F or F given E? Which one is applicable?
F given E.
F given E. The second happening given first has happened. That's the only one we can find. F given E is the one we can find. So this is the formula I'm going to use. So let's find probability of F given E. That means given that first is woman, the probability that second is man. What is that?
9 over 13.
9 over 13 is right. Because the first is woman, so all the men are still there. So 9 men out of 13 people. Probability of E, I had to find and multiply. What is probability of E?
5 over 14.
5 over 14. There are 14 people, 5 of them are women. So this product will be the answer. And if I want to use exercise 6 says, do this by counting technique. Very similar to the earlier problem we did with the marbles. Now it's people, that's the only difference. So if I'm using counting technique, again, this has order. The first has to be woman, second has to be man. So therefore, the order matters, and that means the sample space, count of sample space is all the permutation of 2 taken from 13, 14. From 14, you have to take 2 and rearrange. All the rearrangements have to be counted. So P 13 comma 2, which is equal to factorial 13 over factorial 13 minus 2. And that's equal to 13 times 12. And the count of the event is going to be first woman, second man. So Bach's method, for the first to be woman, there are 5 ways. And for the second one to be man, there are 9 ways. So 5 times 9 ways to get first woman and second man. And so the probability for E is 5 times 9 divided by 13 times 12. Oh. 9 plus 5, and it's not 13 2, it's 14 2, right? I made a mistake. There are 14 people, 9 plus 5. So factorial 14 over factorial 14 minus 2, 12. So it's not, it's 14 times 13. All right, so that's same as the previous answer. All right. There are 300 seniors and 140 are males. And it is known that 80% of males and 60% of females have driver's license. And so those are conditional probabilities given to you. 80% of males have driver's license.
Professor?
Yes.
Sorry, for example 6, was the probability 14-2? Because I think for the rest of it, you included 14, 13, 12, but in probability form, you showed P4-2 still.
Oh, the probability for the event part was correct. It's only the sample space I made a mistake on. For the sample space, I said P13-2, it should have been 14-2 because there are 14 people and you're selecting 2, right?
Okay, I was only able to see the number 4 and 2.
The count of the event was first is woman, second is man. So you need to have a woman and a man in that order. So there are 5 ways to fill that and 9 ways to fill this. 5 women are there, 9 men, right? And that didn't change. Only the count of sample space was permutation of 14, 2, because 9 plus 5 is 14. I did 13 by mistake. That was the only one that was wrong. Okay.
Okay, no problem. Thank you.
So let's do the exercise 7. The question is, if a student is selected at random, what is the probability that the student is a male with driver's license? So probability for male intersection driver's license, that's the question. So to find that, I need to find, I can apply the formula, probability for, what conditional probability do we know? Is it male given D or D given male? If you look at the 80% of males have driver's license, which means given male, 80% have driver's license. That's a conditional probability there. 80% is the conditional probability that the student has driver's license given the student is male. So probability for driver's license given male is the one we know. So multiply that by probability of male to get the answer to the question. So probability for driver's license given male is 80%, 0.8. Probability for male, okay, what is the probability for male? Anybody? What is the probability that the randomly selected student is a male?
140/300.
Right, because there are 140 males out of 300 students. So this product will give you the answer to the first question. Second question is probability for female without driver's license. So that'll be female intersection D bar, no driver's license. Okay, so that will be equal to probability of, which one should I write? Which conditional probability do we know? D bar given F, we know. So D bar given F should go first times probability of F. Okay, probability of D bar given F means given it's a female, what is the probability she doesn't have driver's license? Anybody? What's the number?
0.4.
40%. So you say 60% of the female have driver's license. That means 40% of the female don't have driver's license. So probability that no driver's license given female is 0.4, 40%. Multiply that by probability for the student to be female would be what?
160/300.
Right, 160/300. And if you multiply that, that'll be your answer for that. So you have to interpret those as conditional probabilities. Then you will be able to find the answer. All right, we'll have to stop here. We're out of time. We will continue. We are actually finished. This is just an additional exercise for you. We just don't have the time to finish that. And that exercise is very similar to this exercise we just did. So that finishes this. These exercises are for additional practice for you and not for going over in class. Those are additional practice. So we're done. We just didn't have time to do this exercise. And so you will have problems on all of these. And we are going to do the next handout in the next class, and that is going to be the test material. So my schedule for the test is next Wednesday, and still going to be the same. I don't see a reason to change that. So test is still next Wednesday, 1 week from today. Next Monday, I'll take questions on your printed practice test or online practice test, WebAssign practice test. I haven't posted WebAssign practice test yet. I will be posting it soon, but you're supposed to be working with the printed practice test at this point.